Right now, our galaxy is on a collision course with an entire galaxy, and the thing heading straight for us is far bigger than anyone predicted. James Webb changed everything we thought we knew. What it found is stranger and more dangerous than scientists ever calculated. A hidden black hole firing stars at us like bullets. A sleeping giant about to wake at the center of our galaxy. And a collision that has already begun. We will take you through a warped galaxy, a stolen stream of gas spanning the entire sky, and a moment that rewrites the story of our universe. If you enjoy this journey, hit like and subscribe. It means everything. Now, take a breath. We launch into the deep, look up at the southern sky on a truly dark night, far from any city, and you will see it. A soft glowing smear of light, hanging in the heavens like a patch of cloud that refuses to move with the wind. Ancient sailors spotted it on long ocean voyages and thought exactly that. Cloud. A strange, fixed cloud that stayed in the same place every night, ignoring every weather pattern around it. They named it after the explorer Ferdinand Magellan, who described it during his voyage around the world in 1519. They had no idea they were looking at an entire galaxy. The Large Magellanic Cloud is a dwarf galaxy, a spinning system of billions of stars, ancient gas clouds, and invisible dark matter, sitting roughly 160,000 light-years from Earth. To picture that distance, imagine shrinking the Milky Way down to the size of a football field. The Large Magellanic Cloud would be sitting in the bleachers just outside the 50-yard line, close. By cosmic standards, practically next door. For most of human history, astronomers treated it as harmless. A small companion, drifting in a wide and stable orbit around our galaxy, never causing trouble. Scientists filed it under satellite galaxies, a label that implies something minor, a tag that said, interesting, worth watching, but no action required. That comfortable assumption shattered when better instruments arrived. Scientists began measuring the speed of the Large Magellanic Cloud with greater precision than ever before. What they found was troubling. This galaxy was moving at over 250 miles per second. That is the speed of something thrown hard through space, not something drifting peacefully in a stable orbit. At that velocity, the Large Magellanic Cloud should have escaped our gravitational reach entirely long ago and vanished into the intergalactic void between galaxy clusters. So why had it not? The answer forced a complete rethinking of what this galaxy actually is. Researchers ran new simulations with better models and discovered that the Large Magellanic Cloud was carrying nearly twice as much dark matter as anyone had previously calculated. It was a massive, fast-moving object, heavy enough that our galaxy's gravity had already caught it, locked it into a decaying orbit, and set it on a path with only one possible destination. Think of a marble rolling toward a drain. Once it crosses a certain point, the drain wins. The marble has no choice. It spirals inward. There is no recovering from the pull once that threshold is crossed. The Large Magellanic Cloud crossed that threshold long before any human looked up and called it a cloud. The consequences of something that massive, falling toward a galaxy the size of the Milky Way, go far beyond the distant, abstract future most people imagine when they hear numbers like 2 billion years. Because James Webb's first detailed look at this incoming galaxy revealed that the damage has already started in ways nobody expected to find. Something even stranger was waiting inside it. And finding it required following runaway stars backward through 160,000 light-years of space. Before that story can be told fully, one more piece of the foundation has to be laid. Because the reason the Large Magellanic Cloud is so dangerous is not just its speed, it is how much of it was invisible to us for so long. The name tells you everything, and everything about the name is wrong. Dwarf galaxy. Those two words carry a specific implication: small, lightweight, minor. The kind of object astronomers catalogue and then move on from, because there are bigger, more dramatic things to study. When scientists first measured the Large Magellanic Cloud, the name shaped what they were willing to believe about it. They looked at the stars they could see, added up the gas clouds, estimated the total mass, and arrived at a number that felt reasonable, roughly 1/100th of the Milky Way's mass, small enough to be safely ignored in long-term calculations, small enough to be a footnote in the story of our galaxy's far future. The problem was that those early measurements were only counting part of the story, the visible part. And the visible part of any galaxy is a small fraction of what is actually there. The overwhelming majority of a galaxy's mass is something that produces no light, reflects no light, and interacts with nothing that any traditional telescope can detect. Scientists call it dark matter. It fills the space surrounding every galaxy like an enormous invisible sphere, a halo extending far beyond the outermost visible stars. And because it cannot be photographed, it can only be inferred from the gravitational effects it produces on the things that can be seen. That makes it easy to underestimate. Very easy. When researchers applied more sophisticated models to the Large Magellanic Cloud, tracking the precise motions of stars within it and analyzing how nearby structures responded to its gravitational presence, they arrived at a completely different number. The dark matter halo surrounding this dwarf galaxy was almost twice as large as previous estimates had assumed. That single correction changed everything downstream. A galaxy with nearly twice the expected dark matter is a serious gravitational force, capable of distorting the structure of much larger galaxies around it, heavy enough to drag enormous quantities of gas through space as it moves, and most critically, massive enough that once a larger galaxy's gravity captures it, escape becomes impossible. The orbit begins decaying immediately. Each pass bleeds away more energy. Each orbit draws the galaxy closer to the one that caught it. Scientists published this revised mass estimate, and the field shifted almost overnight. What had been treated as a comfortable, far-future theoretical scenario became urgent and real. The timeline compressed from something abstract into something with a measurable and fixed endpoint. The revised mass also meant the damage already done was greater than anyone had accounted for. If the Large Magellanic Cloud was this heavy, its first close approach to our galaxy had already left physical marks on the Milky Way's structure, marks that should exist in the data. When astronomers looked for them, they found exactly what the new calculations predicted. The question stopped being whether the collision would happen. It became how extreme the collision would be, and as more pieces of the picture came together, the answer kept moving in one direction, more extreme than anyone had been willing to say out loud. And a discovery made inside that galaxy in 2025 made every previous estimate look conservative. Before that discovery can be fully understood, something even more immediate needed to be established. The collision was not just coming. Parts of it had already been happening for a very long time, and the evidence was written in the sky above us. Most people imagine the collision as a future event, 2.4 billion years away, they say, a number so enormous the Milky Way far beyond its visible stars. It has already made its closest approach to our disk, and the physical wreckage from that encounter can be measured by instruments pointing at our own sky today. When the Hubble Space Telescope examined the Large Magellanic Cloud in detail, scientists found something striking and deeply unsettling. The dwarf galaxy's own surrounding gas, the protective envelope that had surrounded it for billions of years, was mostly destroyed. Nearly 90% of it had been stripped away, ripped off and blown back into space by the pressure of our galaxy's own halo slamming against it as the two systems met at their boundary. One researcher described our galaxy as behaving like a giant hairdryer, blasting the gas off the smaller cloud as it rushed inward. The comparison stuck because it is accurate to what the data shows. What remained in the wake of the Large Magellanic Cloud was a vast, sweeping trail of stolen gas, shaped like a comet's tail, stretching across hundreds of degrees of sky. Scientists can map this structure. It is real, it is enormous, and it is actively falling into our galaxy right now. Slowly, over millions of years, this gas rains down into the Milky Way. It settles toward the disk. It mixes with the gas already there. It becomes raw fuel for new generations of stars forming inside our galaxy from material that once belonged to our incoming neighbor. So, when someone says the collision happens in 2 billion years, they mean the final merger, the blending of two galactic cores into a single combined structure. The gravitational pushing and pulling, the stripping of gas, the warping of the disk, the physical reshaping of both galaxies, that process began long before any human was alive to notice it. And it is ongoing every single day. James Webb, with its ability to cut through gas and dust using infrared light that human eyes cannot detect, is now revealing exactly how deep those changes already run. And the first thing it found is still over 100,000 light-years away. Stars stripped from the incoming galaxy are already inside our halo. The future event everyone describes is already a present-tense reality, unfolding in the sky above us every single day, whether anyone is watching or not. James Webb sees the universe differently than any telescope ever built before it. It detects infrared light, wavelengths too long for human eyes to register. That single capability changes everything, because the universe is saturated with dust. Thick clouds of it hang inside galaxies, between stars, inside the dense nurseries where new stars are born. Visible light cannot pass through these clouds. Every telescope built before Webb ran into that barrier repeatedly. The most active and scientifically important regions of any galaxy sat hidden behind dust curtains that no camera could penetrate. Infrared passes through dust as though it is barely there. When Webb turned its mirror toward the large Magellanic Cloud, it was seeing past the curtain for the first time. Into the interior, into regions that had existed in decades of scientific data only as fuzzy, unresolved signals without clear structure. The first major target was a massive star-forming complex in the less explored southwestern portion of the cloud. Researchers had known something was there from earlier surveys, but the details were hidden. Webb revealed it fully for the first time. A region spanning roughly 1,600 light-years, filled with thousands of newborn stars still cocooned inside the gas and dust that gave them birth. Caught in the act of emerging into the universe for the very first time, what surprised the research team most was the rate. This region was producing new stars at twice the efficiency of the Tarantula Nebula, the most famous and most intensively studied star-forming area in our cosmic neighborhood, long considered the benchmark for extreme stellar activity. Twice the rate, in a region that had barely been examined before Webb arrived. The data suggested the reason was the collision itself. The gravitational pressure of the Milky Way squeezing against the large Magellanic Cloud was compressing gas inside it, pushing those clouds past the density threshold required to collapse and ignite as stars. Our approaching neighbor is already responding to us physically. The merger is generating new stellar birth on the other side right now. Webb also revealed something unexpected in the chemical profile of these star-forming regions. The gas inside the large Magellanic Cloud contains far lower concentrations of heavy elements compared to gas clouds in our own galaxy. Less oxygen, less carbon, less of everything that accumulates in galaxies across billions of years of stellar evolution and the explosive deaths of massive stars. This makes its chemistry strikingly similar to what conditions looked like in the very early universe, when galaxies were raw and young and just beginning to build complexity for the first time. Studying these regions gives scientists two breakthroughs at once: a nearby collision unfolding in real time, and a window into how galaxies behaved at the dawn of cosmic history. Two discoveries layered inside one observation. But the deeper Webb looked into this galaxy, the stranger things became. Because hiding at the very center of the large Magellanic Cloud was something that completely changed the threat calculation for everything coming toward us. To understand what that something is, you first need to understand why nobody found it for so long. The large Magellanic Cloud has been observed for centuries. Thousands of research papers have been written about it. And yet the object at its center remained hidden until researchers thought to look at it through the lens of runaway stars flying at millions of miles per hour across the space between galaxies. For as long as astronomers had studied the large Magellanic Cloud, one question sat quietly in the background, asked occasionally and then set aside without urgency. Did it have a supermassive black hole? Most large galaxies do. The Milky Way has one at its center, a compressed mass roughly 4 million times heavier than our star, known as Sagittarius A star. The Andromeda galaxy has one significantly larger. Virtually every major galaxy in the observable universe appears to host one of these gravitational titans, lurking at its core, shaping the behavior of stars for thousands of light years in every direction around it. The large Magellanic Cloud was supposed to be different. Smaller galaxies, the prevailing thinking went, did not necessarily produce the conditions required for supermassive black holes to form or persist. The assumption was that below a certain size threshold, you simply would not find one. Nobody looked very hard for it, because nobody expected to find anything worth looking for. That assumption collapsed under the weight of evidence in 2025. The discovery came from an entirely unexpected direction. Scientists had been studying hypervelocity stars for years. These are stars moving so fast they will escape the Milky Way's gravity entirely and sail off into intergalactic space forever, never returning. They travel at several million miles per hour. Our own star orbits the galactic center at roughly 500,000 miles per hour. These runaways move 6 to 10 times faster than that. The accepted explanation for where they came from was well tested and widely accepted. When two stars orbiting each other drift too close to the supermassive black hole at our galactic center, the extreme tidal forces tear them apart. One gets captured into a tight new orbit around the black hole. The other gets hurled outward with all the energy that had been binding the pair together, released in an instant and launched at enormous speed. Researchers traced the flight paths of 21 of these runaway stars backward through space with extraordinary precision. Using positional data from the European Space Agency's star mapping satellite, every single one was expected to trace back to the center of the Milky Way. Half of them did. The other half traced back to a completely different location. The center of the large Magellanic Cloud, 160,000 light years away. Something inside that dwarf galaxy had been tearing star pairs apart and firing the survivors at our galaxy for millions of years, across an ocean of space that barely fits inside the human imagination. Only one mechanism in the known universe can operate that way. A supermassive black hole, sitting inside our nearest galactic neighbor, undetected, unfound, operating in complete darkness while every telescope in the world pointed at it and saw nothing unusual. The lead researcher at Harvard called the discovery astounding. A monster black hole hiding practically under their noses. The entire time, humanity had been watching the sky and calling it a cloud. And what that hidden black hole is going to do when its host galaxy finally reaches ours leads somewhere far darker than anyone initially imagined. But first, the question of exactly how big this hidden giant actually is, because a black hole discovered is one thing. A black hole measured is something with real, calculable consequences for the future of both galaxies. Discovering the black hole was only the first step. Measuring it was what came next. Scientists used the speeds of the identified hypervelocity stars and the ratio of how many were ejected from our galaxy versus from the large Magellanic Cloud to calculate what the hidden object must weigh. The math converged on an answer. Roughly 600,000 times the mass of our star. 600,000 solar masses. That places it firmly in the supermassive category by any scientific standard. For context, the black hole at the center of the Milky Way, Sagittarius A star, weighs in at approximately 4 million solar masses. So the newly found black hole is smaller than ours. But smaller is not the same as harmless, and size alone is not what makes it consequential. Position matters, and its position, sitting inside a galaxy already locked in our gravitational grip and spiraling closer with every passing million years, makes it one of the most important individual objects in our entire cosmic neighborhood. The lead researcher at Harvard and Smithsonian described the moment of realization. Astounding to have another supermassive black hole just down the block. Cosmically speaking, hiding practically under their noses the entire time. The weight of that statement deserves a moment. The Large Magellanic Cloud is one of the most frequently studied objects in all of astronomy, visible to the naked eye from the southern hemisphere every clear night, observed by professionals and amateurs across centuries of recorded science, mapped, photographed, catalogued, and discussed in thousands of published research papers, and the black hole at its center remained completely invisible the entire time, until researchers thought to trace runaway stars backward through space, the way investigators reconstruct the trajectory of a bullet by examining where it landed and the angle of entry. The universe conceals things in plain sight with extraordinary patience. Now, the stakes rise sharply. When the Large Magellanic Cloud fully merges with the Milky Way over the next 2 billion years, these two black holes will not simply coexist quietly inside the combined galaxy. Gravity does not allow peaceful coexistence between objects of this scale when they find themselves in the same space. The two black holes will find each other eventually. They will begin orbiting one another in a slow gravitational waltz that tightens over millions of years, as each orbit loses a small amount of energy to gravitational radiation. Eventually, they will collide, and the energy released by that final merger will take a form unlike any ordinary astronomical event. Gravitational waves, actual ripples in the fabric of space and time itself, radiating outward in every direction at the speed of light, the most powerful event our galaxy will ever generate, measured in any unit of energy. But that collision of black holes is billions of years away. Something far more immediate is already being set in motion right now, something that involves the black hole at the center of our own galaxy, and the moment it is forced to stop sleeping. Because the Large Magellanic Cloud is not only bringing a supermassive black hole with it, it is bringing an enormous supply of gas that will, over millions of years, be funneled toward our own galactic center and delivered directly to the sleeping giant waiting there. When that delivery arrives, everything changes. At the center of the Milky Way, 26,000 light-years from the ground beneath your feet, something ancient and enormous is waiting in the dark. It is called Sagittarius A star, our galaxy's supermassive black hole. 4 million solar masses of matter compressed into a region of space smaller than our solar system. By the standards of the wider universe, it is not particularly large. There are black holes billions of times more massive lurking at the centers of distant galaxies. But it is ours, and right now, compared to those distant behemoths, it is almost completely quiet. Astronomers describe it as a sleeping giant. It consumes barely any gas. It fires no visible jets of energy into surrounding space. It produces only rare and brief flickers of X-ray light when an errant cloud of material drifts too close and gets torn apart. For the scale of object it is, Sagittarius A star is remarkably still. That stillness has a history, and the history is not as peaceful as the present suggests. Evidence buried in the structure of our own galaxy tells a different story about the past. Enormous cone-shaped bubbles of hot, energetic gas extend above and below the galactic center, stretching tens of thousands of light-years in both directions. Discovered by the Fermi Space Telescope and confirmed by subsequent observations, these structures were not created by anything quiet. a massive energy release from the galactic center, almost certainly from Sagittarius A star feeding intensely, carved them into the surrounding galaxy a few million years ago. The sleeping giant woke before. It fed, it blazed, then it went quiet again. The large Magellanic Cloud is going to wake it a second time, and based on what the simulations show, the feast this time will be vastly larger. Here is the mechanism. As the merger unfolds across millions of years, enormous quantities of gas and stars from the large Magellanic Cloud will be progressively funneled toward the center of the Milky Way. This material does not fall straight in immediately. It swirls, forms dense structures, piles up at the gravitational boundary surrounding the black hole. But eventually, inevitably, it crosses the point of no return and falls inward. A black hole grows by consuming mass. More mass means more growth, and more growth, fed continuously by the material arriving from the merger, means more radiation as the infalling gas heats to extreme temperatures at the boundary. Simulations run by astrophysicists at Durham University predict that Sagittarius A star could expand to roughly 8 times its current mass as the collision plays out. At 8 times its current size, our galactic center would transform into something astronomers call an active galactic nucleus. At its most extreme, a quasar, a feeding supermassive black hole, can outshine the combined light of an entire galaxy of hundreds of billions of stars. Our own galactic center could become one of those blazing objects. If that happens, the center of the Milky Way will be a permanent radiant beacon in the sky, day and night, visible from any planet in the galaxy with a clear sightline for millions of years continuously. And something even more immediate than that is already happening above our heads right now. Runaway stars moving at millions of miles per hour are crossing the space between the two galaxies as this plays. They left the large Magellanic Cloud long ago. Some of them have already arrived. Picture a spinning carnival wheel loaded with rocks instead of prizes. Now picture someone cutting the brake while it is moving at full speed. The rocks fly outward in every direction, fast and uncontrolled, traveling as far as the force behind them can carry them. Some travel for miles. A supermassive black hole does something structurally similar to pairs of stars, and the result is one of the most violent individual events that can happen to a single star anywhere in the known universe. When 2 stars orbiting each other drift into the gravitational territory surrounding a supermassive black hole, that black hole does not treat them equally. Its gravity is so extreme and so asymmetric across even the small distance separating the 2 stars that it grabs one and flings the other. The captured star spirals inward into a tight new orbit. The ejected star receives an enormous burst of energy. All the binding energy that had been holding the pair together released in an instant, launching it outward at millions of miles per hour. These are hypervelocity stars, and confirmed research published in 2025 established that the supermassive black hole inside the large Magellanic Cloud has been running this process across millions of years of cosmic time. 9 of the 21 hypervelocity stars examined by researchers traced their origins to the large Magellanic Cloud, 160,000 light-years away. These stars were born inside that dwarf galaxy. They spent millions of years living there, fusing hydrogen in their cores, moving through the cloud with all the other stars around them. Then they wandered too close to the hidden black hole, and they were launched across an ocean of intergalactic space at speeds that carried them all the way into the outer reaches of our galaxy. They arrived here as strangers, stars from another galaxy, embedded now inside ours, still moving outward through the halo on trajectories they will never slow down from. Scientists found these stars clustered in a specific patch of sky near the constellation Leo. That clustering was the critical clue that allowed the researchers to build their model. If a supermassive black hole existed inside the large Magellanic Cloud, and if the cloud was moving around our galaxy in the orbit already measured precisely by the Gaia satellite, Then, the stars it ejected would receive an extra speed boost from the cloud's own motion through space. Stars launched in the forward direction of travel would move fastest, travel farthest, and appear concentrated in one specific region of the sky as seen from Earth. The observed distribution matched the prediction with striking precision. Those stars are permanently part of the Milky Way's outer halo now. They are moving outward and will eventually escape into intergalactic space, carrying with them physical evidence that the large Magellanic Cloud has been reaching into our territory for millions of years, leaving fingerprints across our galaxy long before any human gave it a name. Stars being fired across space at us are one visible consequence of what is happening. But something far more subtle is simultaneously reshaping the entire visible structure of the Milky Way itself, and it is stranger than individual stars crossing space. The shape of our galaxy is changing, the disk is bending, and the force doing the bending is still over 100,000 light years away. Picture the Milky Way as a flat, spinning disk of stars. A vast pinwheel, hundreds of thousands of light years across, rotating steadily through the dark with the slow, majestic regularity that makes it feel permanent and eternal. Now picture something very heavy moving through the space beneath one edge of that disk, close enough for its gravity to reach upward and pull unevenly on different parts of the structure from below. That is what is happening to our galaxy right now. Today, the outer regions of the Milky Way's disk are warped. Scientists discovered this decades ago. The galactic plane does not lie flat. It curves upward on one side and tilts downward on the other, bent out of its expected shape like the brim of a hat that has been twisted unevenly. Astronomers measured it, mapped it carefully, debated its origin across many years, and proposed a range of possible causes. The most compelling and well-supported explanation, built on data from multiple recent surveys, including the Gaia satellite and large ground-based programs, points directly at the large Magellanic Cloud. As this massive galaxy moves through the outer halo of the Milky Way, its gravitational pull does not act uniformly across our disk. The regions of our galaxy sitting closer to it feel a stronger tug. Regions farther away feel a weaker one. The difference in force across the full span of the outer disk creates a bending effect, a slow torque that tilts and curves the disk material away from the flat orientation it would maintain in the absence of an external force. When researchers modeled the large Magellanic Cloud's trajectory and calculated the gravitational effects it would produce on the outer disk, they reproduced the observed warp shape with accuracy that is difficult to attribute to coincidence. The warp is where the models predict it should be, with the orientation predicted at roughly the magnitude predicted. Confirmed. The outer disk of the Milky Way has been physically deformed by the gravitational influence of a galaxy that has not even fully arrived yet. The deformation goes beyond the large-scale warp. Observations reveal wave-like oscillations rippling through the disk material itself. The Milky Way's gas layer has corrugations, periodic variations in density and height, propagating outward like rings spreading across a pond. The timing and location of these oscillations are consistent with a major external gravitational disturbance arriving within the past few 100 million years, which matches the calculated timing of the large Magellanic Cloud's first close approach. Stars in the outer disk have also been mapped moving in complex patterns, deviating from simple circular orbits. Their velocities carry the signature of a system disturbed and not yet settled back into equilibrium. Every model astronomers built of the Milky Way before the large Magellanic Cloud's true mass was understood is now considered incomplete. The galaxy we thought we lived in is being actively reshaped right now by forces that earlier calculations simply ignored. The warp is the most visible scar. Below the visible surface, something stranger was found hiding in the invisible matter that surrounds our galaxy, something that connects this collision to the deepest unsolved problem in all of modern physics. And to understand it, you first need to picture a ship moving through an ocean that is completely invisible to any camera or sensor, leaving a wake behind it that can only be detected by watching how the surrounding water causes floating objects to cluster in unexpected patterns. Chapter 10. The Magellanic Stream. Stretching across the sky in an enormous sweeping arc, there is a structure so vast it spans nearly the entire visible sphere of the heavens, as seen from Earth. You cannot see it with your eyes. It is made of gas, mostly hydrogen, invisible to any optical telescope. But instruments tuned to radio wavelengths reveal it in striking detail. What those maps show is one of the most dramatic physical records of the violence already underway between our galaxy and its approaching neighbor. Scientists call it the Magellanic Stream. It sweeps across roughly 300 degrees of sky. That is nearly a complete circle of the heavens, an arc of stolen gas trailing behind the Magellanic Clouds, like an enormous ribbon of material that once belonged somewhere else entirely. The stream was pulled away from the Magellanic Clouds over billions of years by a combination of forces acting simultaneously from different directions, the Milky Way's gravity reaching outward and pulling on the gas from one side, the interaction between the large and small Magellanic Clouds stirring and disturbing the gas from within, each galaxy pulling on the other's outer material as they traveled together through space, and the pressure of our galaxy's own hot surrounding halo acting like a persistent, steady wind against the incoming clouds, stripping layers from their outer regions and blowing the material back into a long, sweeping tail behind them. What Hubble revealed, and what Webb has now examined with greater infrared resolution, is that this stream is actively falling into the Milky Way. Gas from the stream is raining down into our galaxy right now. Slowly, over millions of years, this stolen material sinks toward the disk and eventually becomes raw fuel for new generations of stars. Scientists estimate the stream contains enough hydrogen to sustain star formation inside the Milky Way for at least 5 billion additional years. 5 billion years of extra fuel, delivered freely by the galaxy that is simultaneously racing toward us to reshape everything we know about our home. The stream also carries heavy elements: oxygen, carbon, and nitrogen forged inside stars that lived and died within the Magellanic Clouds across billions of years, then expelled into the surrounding gas by explosive stellar deaths. As this enriched material falls into our galaxy, it mixes with the Milky Way's own chemical history. Future stars born from this combined reservoir will carry the chemical heritage of two galaxies inside every atom of their cores. There is something worth sitting with in that image. The galaxy heading toward us to collide is simultaneously feeding us, enriching us, and giving us the material to keep building new stars even as it approaches to transform everything. Webb's infrared sensitivity has revealed structures within the stream, suggesting the stripping process is more layered and complex than earlier radio-only maps had indicated. Some regions of the stream appear to have been stripped in separate events at different times, recording the history of multiple close passes rather than a single continuous flow. And deep inside the large Magellanic Cloud itself, in the places where stars ignite at rates our galaxy cannot approach, Webb found something that rewrote the standard for what extreme stellar creation actually looks like up close. What it saw there was so active, so intense, and so different from anything inside our own galaxy that researchers had to build new frameworks just to describe it properly. If there is one place in the known universe where you can watch the raw violence of stellar creation in real time, it is a region inside the large Magellanic Cloud called the Tarantula Nebula, named for the spider-like filaments of glowing gas reaching outward from its blazing center. This region spans roughly 1,000 light-years from edge to edge. It contains some of the most massive and luminous stars ever confirmed anywhere near our galaxy. Astronomers calculated that if it sat at the same distance from Earth as the Orion Nebula, our nearest major star-forming region, it would be bright enough at night to cast shadows on the ground. You could read by its light. Before James Webb, images of the Tarantula Nebula existed from many telescopes, Hubble had photographed it. Radio and X-ray instruments had mapped different aspects of it, but the most active inner regions remained hidden behind thick curtains of gas and dust that blocked every camera seeing invisible light. The heart of one of the most spectacular objects in our cosmic neighborhood had never been clearly seen. Webb changed that. When it turned its mirror toward this region, the science team described the results as jaw-dropping. Thousands of previously invisible stars appeared in the data, young stars still surrounded by the glowing cocoons of gas and dust from which they were born, caught at the earliest stages of stellar life before they had cleared the material around them and become visible to ordinary telescopes. At the core of the nebula, the most massive stars produce radiation so extreme it is physically carving, expanding bubbles through the surrounding gas. Their stellar winds, streams of charged particles traveling at thousands of miles per second, push outward in all directions, compressing the gas at the bubble walls. At those compressed edges, density rises past the threshold where gravity takes over, and new stars collapse inward and ignite. Stars creating the precise conditions for more stars. A self-reinforcing cycle of creation, powered by the destruction it produces at each turn. Webb also revealed long, cool filaments of dense gas threading outward from the center through the hotter surrounding material. Some of these filaments extend for hundreds of light years. They are the next generation of stars in waiting, slowly gathering mass from the surrounding environment until gravity pulls them past the point of no return. One finding challenged existing models of stellar formation. The ratio of low-mass stars to high-mass stars being produced differed from what theory predicted for an environment this extreme. More smaller stars were forming relative to massive ones than the equations expected. Even in the most energetic star factory in the local universe, the physics of birth produces surprises that existing models do not fully explain. When the large Magellanic Cloud merges with the Milky Way, this entire self-reinforcing engine of stellar creation will become part of our galaxy. The compression waves from the merger will trigger new bursts of stellar birth across enormous regions of space that currently have nothing like this activity. Another discovery inside the large Magellanic Cloud connects this story to an event that already changed astronomy forever, and that James Webb is still watching continue to unfold. It began on a specific night in 1987, and it began without light. An invisible burst of particles passed through the entire Earth before any telescope saw anything at all. 2 billion years sounds like it removes all urgency from the story. Put that number next to a human life, a civilization, or even the entire span of recorded human history, and it dissolves into abstraction. It sounds like a problem stored safely in the far distance, with no connection to anything alive or anything that currently matters. People hear the number and move past it, but scale it differently. Our galaxy is 13.5 billion years old. The large Magellanic Cloud has been traveling the cosmos for nearly as long. Both of these ancient structures have existed across most of the universe's entire lifespan, and the full merger of their cores, the blending of their stars and gas and black holes into a single new combined structure, is arriving in just 1/7 of the time either galaxy has already existed. On the scale of cosmic history, 2 billion years is soon. Astronomers have run the simulations many times, using different mass estimates, different dark matter distributions, different orbital parameters, and different assumptions about the gravitational influence of nearby galaxy groups. The result is consistent across all of them. The large Magellanic Cloud is falling inward. The merger will happen. The only remaining variable is the precise sequence and character of the violence involved. Here is what the simulations most consistently show. In roughly 2 billion years, the large Magellanic Cloud will make a second close approach to our galaxy, far more destructive than the first. Tidal forces during this pass will begin pulling the dwarf galaxy apart structurally. Stars from across its body will scatter into enormous arcs around the Milky Way, some falling into the outer disk, others flung into the halo, spread across volumes of space that are currently empty of any significant stellar population. Over hundreds of millions of years following that pass, the remnant will spiral progressively deeper into our galaxy on each successive orbit, losing more energy to the friction of moving through the Milky Way's surrounding material, its structure continuing to dissolve. Eventually, the core of the large Magellanic Cloud, carrying its 600,000 solar mass black hole, will sink toward the center of the Milky Way. There, the two black holes will find each other. They will orbit. They will spiral closer across millions of years, and the gravitational waves released when they finally merge will travel through the fabric of space in every direction at the speed of light. Simultaneously, fresh gas funneled toward the galactic center will feed Sagittarius A star into a state of intense and prolonged luminous activity, visible as a blazing beacon at the heart of our galaxy. There is also a small but scientifically acknowledged possibility that extreme gravitational disturbances during the merger could nudge our solar system into a different position within the galaxy. The probability is low. Researchers do not assign it 0. James Webb has given scientists the sharpest picture yet of what is approaching. And what that telescope revealed about the companion galaxy traveling alongside the large Magellanic Cloud adds a dimension to this story that no simulation had fully captured before the observations arrived. Because the large Magellanic Cloud is destroying its traveling companion in real time, confirmed by data published in 2025, a galaxy being torn apart while it moves, even before reaching us. The three-body collision was never in the textbooks. The large Magellanic Cloud arrived with company. Traveling alongside it, at a distance of roughly 200,000 light-years from Earth, is a smaller and quieter companion called the Small Magellanic Cloud. Both galaxies have drifted through our cosmic neighborhood together for billions of years, gravitationally linked to each other and, to varying degrees, caught in the influence of the Milky Way's gravity. The relationship between the two companions was never equal. The large Magellanic Cloud carries far greater mass. It has the stronger gravitational grip, and scientists confirmed in research published in April of 2025, using data the team described as indisputable, that the larger companion is actively and irreversibly destroying the smaller one. The discovery came from tracking more than 7,000 massive young stars inside the Small Magellanic Cloud using precision velocity data from the European Space Agency's star mapping satellite. The researchers expected to find the signature of a coherent galaxy: rotation. Stars moving in an organized pattern around a shared center of mass, the way water circles slowly in a bowl. Even irregular dwarf galaxies show some organized rotation. What the data showed was the opposite. Stars on one side of the Small Magellanic Cloud were moving toward the large Magellanic Cloud. Stars on the other side were moving away from it. The galaxy was being stretched in two directions simultaneously, pulled apart along competing axes by gravitational forces its own mass was too weak to resist. The team leader at Nagoya University said the result was so unexpected that the researchers assumed an analysis error and checked everything multiple times. The result held every time. What made the finding even more significant was the absence of rotation. Young, massive stars in any coherent galaxy should share the rotational motion of the gas clouds they were born from, because they are too young to have drifted far from their birth locations. These stars showed no rotational pattern. The gas itself was no longer rotating. The internal structure of the entire galaxy had been its stars, its gas, and its identity as a distinct structure. By the time the large Magellanic Cloud fully merges with the Milky Way, the smaller companion may already be gone, absorbed, and erased. The material being stripped away is joining the broader flow of gas and stars already heading in our direction. So the collision approaching us involves three galaxies in motion simultaneously, one consuming the second, even as both are caught by the gravitational reach of the third, each system reshaping the others at the same time. And while this three-body event plays out in the surrounding space, something equally dramatic is happening inside the Milky Way itself, at a structural level that most people have never encountered in any account of this story. The Milky Way is not just a passive bystander being approached by an intruder. It is actively responding. Its disk is moving. Its center of mass has shifted. The entire galaxy is behaving like a structure that has already been struck, because in a real and measurable sense, it has. The large Magellanic Cloud did not announce its approach politely. It pushed, and the Milky Way pushed back, and both galaxies are still absorbing the consequences of an encounter that happened in the cosmic recent past. The Milky Way is moving in a direction it should not be. The disk of our galaxy, the flat spiral structure containing our solar system and hundreds of billions of other stars, is drifting with respect to the outer halo surrounding it. The inner galaxy and the outer galaxy are out of sync, moving relative to each other in a way that only makes sense if something large has recently disturbed the entire system from outside, and the system has not yet finished responding. Scientists call this reflex motion, and it has been directly measured in the velocities of real stars in the Milky Way's outer halo. Here is what causes it. When the large Magellanic Cloud passed close to our galaxy's disk at speeds exceeding 200 miles per second, its gravitational influence did not act on all parts of the Milky Way equally. Stars and gas in the inner disk felt the pull and began moving toward the intruder. Stars in the outer halo, sitting tens of thousands of light years farther away, have orbital timescales far too long to respond as quickly. They lagged behind. The result is a genuine displacement between the behavior of the inner and outer galaxy. The inner disk moves in a direction that traces back to where the large Magellanic Cloud has already been. The outer halo is still in the process of catching up. Our galaxy is measurably reacting to something that already passed through our neighborhood and moved on. Confirmed. Researchers using data from large sky surveys identified this motion by mapping the velocities of stars in the outer halo at distances between 60 and 100,000 light-years from the galactic center. The direction of motion pointed back along the large Magellanic Cloud's already traveled path with clear statistical significance. The practical consequence of this imbalance is significant. The dark matter halo surrounding our galaxy, the enormous invisible sphere of mass extending far beyond any visible star, has been physically shifted. The center of that halo no longer aligns with the center of the visible disk. The Milky Way's center of mass sits between 15 and 25,000 light-years away from its structural center. We live in a galaxy that is dynamically off-center right now. This matters beyond the intellectual satisfaction of knowing it. Stellar streams, thin rivers of stars torn from ancient globular clusters orbiting through the halo, are some of the most precise tools astronomers use to map the Milky Way's gravitational field. They act like tracer threads, revealing the invisible mass distribution. But the field is changing because of the large Magellanic Cloud's influence, and the streams are bending in ways that do not match any model built before the true mass of our neighbor was understood. Every gravitational map of our galaxy, constructed on older data, requires revision. The galaxy we thought we understood is not what we actually live inside, and the most extraordinary evidence of what is happening comes from something that cannot be seen, photographed, or touched in any way. Something that exists in pure darkness, trailing the large Magellanic Cloud through space like a vast and invisible shadow. Scientists detected it anyway, and what they found in that darkness may turn out to be one of the most important observations in the history of physics, because the wake left behind by our approaching neighbor is not just evidence of a collision, it is a window into the nature of reality itself. Something enormous is following the large Magellanic Cloud through space. You cannot photograph it. You cannot point any camera at it and capture an image. It emits no light, no radio waves, no heat signature, nothing that any detector built to observe electromagnetic radiation can directly record. And yet it is real. It is physically measurable through its effects on the stars embedded around it. And in 2021, scientists published the first confirmed detection of it. It is a gravitational wake, a trail of elevated dark matter density following the path the large Magellanic Cloud has already travelled through our galaxy's halo, the same way a ship leaves churned and compressed water trailing behind its hull as it moves through the ocean. The mechanism is well understood theoretically. As the large Magellanic Cloud moves through the sea of dark matter surrounding the Milky Way, its gravity deflects the dark matter near its path. Those particles swing around it as it passes and then converge in the region just behind where the cloud has been, creating a zone of higher density, a dark matter pileup following the trajectory of the galaxy through space. Physicists predicted this wake should exist years before anyone had instruments sensitive enough to detect it. The detection itself became possible through the stars. Dark matter cannot be photographed directly, but stars follow the gravitational landscape around them. Where dark matter density is higher, stars concentrate in slightly larger numbers. Where density drops, stars spread out. Researchers mapped the distribution of over 1,000 stars in the Milky Way's outer halo. At distances between 60 and 100,000 light-years from the galactic center, and found a region of elevated stellar density sitting exactly where the models predicted the dark matter wake should be. The signal matched the predicted location, and it was even stronger than many simulations expected. That stronger than expected signal provided its own additional piece of information. It is independent evidence that the large Magellanic Cloud is on its very first orbit through our galaxy. If it had passed this way before, previous interactions would have spread and diffused the wake over time. A sharp, strong wake is the fingerprint of a first-time encounter. The wake is also a scientific instrument in disguise. Its precise shape encodes information about what dark matter actually is at a fundamental level. Different theoretical models predict measurably different wake characteristics. Cold dark matter, the model fitting most large-scale cosmological observations, predicts a specific density profile. Warmer, dark matter with faster moving particles produces a different and more spread out structure. An exotic model called fuzzy dark matter, where dark matter behaves as a quantum wave rather than discrete particles, produces something different still, with interference patterns that particle-based models would never generate. By measuring the wake with enough precision, scientists can test these models with a natural experiment running in our own cosmic backyard. Confirmed. The wake exists, and its location matches theoretical predictions. Unknown. Whether its precise density profile confirms cold, dark matter or points towards something more exotic, that question is being actively answered. The invisible is slowly yielding its secrets, and while it does, something very visible inside the large Magellanic Cloud captured the world's attention decades before Webb ever launched from Earth. An explosion so close and so powerful that detectors on 3 continents registered its arrival before a single telescope had seen any light at all. On the 23rd of February, 1987, detectors buried deep underground on 3 different continents registered something that had never been recorded before in the history of science. A burst of neutrinos, subatomic particles so tiny and so weakly interacting that they pass through entire planets as though the rock and metal are not there. These particular detectors had been built for a completely different scientific purpose. What they caught instead was a signal arriving from 160,000 light-years away, reaching Earth before the visible light, because neutrinos travel at nearly the speed of light and experience nothing that slows them down. Hours later, the light arrived. A blue supergiant star in the large Magellanic Cloud, roughly 20 times the mass of our own star, had reached the end of its life and detonated in a core collapse supernova. The explosion released more energy in its first 10 seconds than our star will produce across its entire 10 billion year lifetime. Astronomers named it Supernova 1987 A, and within hours, observatories around the world had turned toward the southern sky. This was the closest observed supernova since before the telescope was invented. Close enough to study in extraordinary detail. Close enough that the neutrino burst arrived measurably ahead of the light, directly confirming what theoretical physicists had long predicted, that the core collapse begins with a neutrino surge, produced when the iron core implodes into a neutron star or a black hole. That had been theory for decades. Confirmed. 1987 turned it into directly observed fact for the first time. The story did not end in 1987. The remnant is still evolving, still changing, still teaching. James Webb has provided the clearest view yet of what a stellar explosion looks like nearly 4 decades after the detonation. When Webb turned its instruments toward the site, it found a glowing ring of gas approximately 1 light-year across. This ring was material the original star had expelled into surrounding space roughly 20,000 years before it exploded. When the supernova shockwave reached this pre-existing ring, it heated the gas to millions of degrees, making it glow intensely across multiple wavelengths. Webb's infrared instruments captured the structure in detail no previous telescope had achieved, revealing individual clumps of material moving outward from the explosion center at thousands of miles per second. Webb also detected dust forming inside the expanding debris cloud. Cold, solid grains condensing from the hot chaos of the aftermath. Grains that will eventually become raw material for new stars and billions of years from now, potentially the building blocks of new planetary systems. At the very center of the remnant, a neutron star likely spins hundreds of times per second. Finding it definitively has been difficult because it sits buried under layers of hot gas, still too dense and bright for any telescope to see through clearly. Webb is actively working toward a confirmed detection. Mystery. The neutron star at the center of supernova 1987 A has not yet been directly confirmed. Its existence is expected and implied by multiple independent signals. Confirming it directly remains one of the active goals of ongoing observations. One star, in a galaxy that will one day merge with ours, is still rewriting what science knows about stellar death nearly 40 years after the explosion that first caught the world's attention. There is a place inside the large Magellanic Cloud where the scale of stellar creation makes every star-forming region in our own galaxy look modest and restrained. It is called 30 Doradus. Astronomers also refer to it as the Tarantula Nebula, a name that has appeared earlier in this story. But the full scale of what is happening inside it deserves its own detailed accounting, because the numbers involved have no equivalent anywhere inside the Milky Way. 30 Doradus spans roughly 1,000 light-years from edge to edge. That alone places it far beyond anything our galaxy hosts in terms of sheer physical scale. But scale is only the beginning of what makes it extreme. At its core sits a cluster of stars that pushed astronomers to the edge of what their classification systems were designed to handle. Some of these stars contain more than 100 times the mass of our star. A handful push toward or past 200 solar masses, approaching the theoretical upper limit for how massive a star can grow before its own radiation begins dismantling it from the inside out. Confirmed. Some stars in this cluster rank among the most massive objects ever directly measured anywhere in the known universe. These are not stable, long-lived objects. Stars this extreme burn through their fuel at rates so fast they will exhaust their entire supply within just a few million years. In the full lifetime of the universe, they are brief and violent flashes. James Webb imaged the interior of 30 Doradus in infrared detail that no instrument had ever achieved before. The results revealed thousands of previously hidden newborn stars, each one still wrapped in the birth cocoon of gas and dust surrounding it, caught in the very earliest phase of stellar existence, before they had begun to push that material away. One finding surprised researchers examining the statistical makeup of what was being born. The ratio of low-mass stars to massive stars being produced differed from what existing theory predicted for an environment this extreme. More smaller, lower-mass stars were forming relative to massive ones than the models expected. Even in the most energetic stellar nursery in the local universe, the physics of star formation produces results that current equations do not fully capture. The most massive stars at the core drive an ongoing cycle. Their radiation carves expanding cavities through the surrounding gas. The compressed walls of those cavities then collapse under gravity and ignite new stars. Each generation of massive stars creates the conditions for the next generation to form, a self-sustaining engine of creation powered by its own destruction. Several stars in 30 Doradus are approaching the end of their lives. Some may have already exploded in the time it takes light to travel from them to Earth. Webb is watching the entire complex continuously. When this galaxy merges with ours, everything in 30 Doradus becomes part of the Milky Way, and the story of what is hidden in the oldest stars of the large Magellanic Cloud adds yet another layer to this history that keeps getting stranger the deeper researchers look. Because not everything interesting about the large Magellanic Cloud is young and blazing and new. Some of the most important things inside it are the oldest objects in the known universe, stars that formed when the cosmos itself was barely 1 billion years old, still burning quietly after 12 billion years of continuous existence, carrying chemical records from an era no instrument has ever directly seen. Every galaxy carries a record of its own past, written in the ages and chemistry of its stars. The oldest stars in the universe formed when the cosmos was young, and the only materials available for building were hydrogen, helium, and traces of lithium. No heavy metals yet. No carbon or oxygen in any meaningful abundance. Those elements had not yet been forged inside stellar cores and scattered by the explosive deaths of massive stars. The first generations of stars burned with a chemistry the universe would never see repeated in quite the same way. Some of those stars still survive. Dim, ancient, iron-poor, burning quietly after more than 12 billion years of continuous nuclear fusion. They are the oldest fossils the universe has produced, and they carry information about conditions that no laboratory on Earth can replicate. The large Magellanic Cloud contains stars like this. Mixed among its blazing nurseries and its clusters of young massive stars are ancient survivors from the earliest epochs of cosmic time. James Webb's extraordinary sensitivity at faint infrared wavelengths makes it uniquely capable of finding and studying these populations in ways no previous telescope could match. When researchers directed Webb toward regions of the large Magellanic Cloud, flagged by earlier surveys as potentially harboring old stellar populations, the data added a new and important layer of complexity to the galaxy's history. The oldest stars in the large Magellanic Cloud are distributed unevenly. They cluster in specific regions, concentrated in ways that strongly suggest the cloud was assembled from multiple smaller components. Early in its history, the large Magellanic Cloud appears to have merged with and consumed even smaller galaxies, incorporating their ancient stellar populations into its own growing structure as it built up mass over billions of years. Confirmed. This interpretation is supported by multiple independent studies using different observational methods and different instruments, including both Webb data and earlier Hubble and ground-based surveys. The clustering pattern and chemical signatures of the oldest stars are consistent with an accretion history involving multiple smaller merger events at different epochs. This makes the large Magellanic Cloud's history a smaller scale version of our own. The Milky Way was built by consuming smaller galaxies across its entire 13 billion year lifespan. Streams of stars from those ancient absorptions still orbit through our halo today, identifiable by their distinct chemical compositions long after the galaxies they came from ceased to exist. When the large Magellanic Cloud is absorbed into the Milky Way, it will bring not just its current stars and gas, but the accumulated debris of every galaxy it consumed during its own long history. Stars from structures that no longer exist anywhere, carrying chemical stories from stellar generations that lived and died before our own galaxy even finished forming its first disk, will all arrive together, packaged inside a single incoming system. Unknown. The precise and full sequence of mergers the large Magellanic Cloud experienced before entering our neighborhood has not been reconstructed completely. Webb is still mapping the ancient stellar populations, building a portrait that may never be finished before the galaxy carrying them arrives. The portrait will be incomplete, because by the time we fully understand it, the galaxy will have ceased to exist as a separate thing, and what the collision means for the one planet in this story that currently has anyone paying attention is the next question worth answering directly. At some point in any story about galaxies colliding, someone asks the question that matters most on a personal level. What does this mean for us? The question deserves a real answer, delivered plainly. The merger of the large Magellanic Cloud with the Milky Way will not destroy Earth. That can be stated with confidence and specificity. The scales involved in a galactic collision from New York to Los Angeles. During a galactic merger, those sand grains drift slowly through each other's clouds in vast and graceful motion. Individual stars almost never actually collide. The space between them is simply too enormous. The direct physical danger to Earth from the stars of the large Magellanic Cloud is, by every calculation scientists have run, negligible. But negligible and zero are not the same thing, and researchers do not stop at the immediate and obvious. Gravitational disturbances during the extended merger process could, over billions of years, shift the position of our solar system within the galaxy. If our current orbital path carries us through the relatively quiet outer spiral arms, a significant perturbation could alter that over time, moving us into a denser, more active region. In such a region, radiation from newly forming massive stars and from the awakened activity of the galactic center would be more intense than what the solar system currently experiences in its current location. There is also a low, but non-zero possibility that gravitational influences during the merger could nudge objects in the outermost reaches of our solar system inward. The vast cloud of icy bodies orbiting far beyond the planets could be disturbed, sending a higher rate of cometary visitors toward the inner solar system over millions of years. These are acknowledged possibilities, assigned low probabilities by researchers, and raised as scientific considerations rather than as practical warnings. All of this unfolds across timescales, measured in billions of years. The Earth may not remain in its current condition across those spans of time, regardless of the galactic merger, given that our own star will be moving toward the end of its own life on similar billion-year timescales. What the collision means for Earth in any immediate or practical sense is nothing at all. What it means for our understanding of the universe is a completely different kind of answer. It means we live inside a cosmos that is continuously violent, continuously building the habitable future of the Milky Way is now uncertain. And the reason it became uncertain is the same galaxy we have been following through this entire story. For decades, when anyone asked what would eventually happen to the Milky Way, astronomers had a single confident answer. Andromeda. In about 5 billion years, the Andromeda galaxy, a massive spiral 2.5 million light-years away and home to roughly 1 trillion stars, had been measured moving toward us at approximately 70 miles per second. The math said it would arrive in roughly 5 billion years and merge with us over several billion more, eventually producing a giant elliptical galaxy that astronomers had already given an informal name, Milkomeda. The story appeared in textbooks. It ran in planetarium programs. It had the settled confidence of a forecast that every researcher agreed on. Then the true mass of the large Magellanic Cloud was established. When scientists re-ran the Andromeda collision models with the revised mass of our neighbor properly incorporated, alongside better measurements of the broader local group of galaxies and updated calculations of the gravitational dynamics across the entire region, the simple picture dissolved. Research, published in 2025, found that the probability of a direct merger between the Milky Way and Andromeda was no longer close to certain. With all the relevant gravitational variables properly accounted for, the models converged on roughly a 50-50 chance of a true merger versus a close pass, where the two galaxies swing past each other and continue on separate trajectories, and if a merger does occur, the revised timeline pushes the event out to at least 8 billion years from now, considerably later than the previous estimate of 5 billion. The collision that had been the defining story of our galaxy's far future is now uncertain, delayed, and by some models entirely avoidable. Meanwhile, the Large Magellanic Cloud, arriving in roughly 2 billion years, has become the most certain, most immediate, and most consequential cosmic event in the Milky Way's foreseeable future. A collision assigned essentially 100% probability by every simulation run to date using current measurements. There is a further dimension worth adding to this picture. Whatever eventually happens with Andromeda will involve a Milky Way that no longer looks like the one we currently inhabit. The merger with the Large Magellanic Cloud will expand our stellar halo to up to 5 times its current size. It will grow the central black hole to up to 8 times its current mass. It will alter the gravitational signature of the entire galaxy in fundamental ways. Whatever structure eventually encounters Andromeda will be a transformed version of what exists today. The Milky Way as it currently is will have been gone for billions of years before Andromeda arrives at its new, reshaped destination. The large collision everyone expected to define our destiny has become uncertain. The smaller collision everyone underestimated has become the certain one. And what that collision is teaching scientists about the darkest and deepest mystery in all of physics goes further than anyone predicted when the dark matter wake was first detected and measured in our outer halo. To understand why, you need to think about what dark matter actually is, why it has resisted every attempt to detect it directly for decades, and why a galaxy crashing through our halo at 250 miles per second turns out to be the best tool scientists have ever had for studying it. The collision is not just reshaping two galaxies, it is running an experiment that no laboratory on Earth could ever replicate. And the results could rewrite physics entirely. Dark matter is the universe's most persistent and maddening secret. It makes up roughly 85% of all the mass in the cosmos. It shapes the structure of everything visible, acting as the invisible scaffolding around which galaxies form and cluster. The large-scale architecture of the universe, the vast web of galaxy clusters and filaments and voids that astronomers map across billions of light years, was built by dark matter, pulling ordinary matter into place during the first billion years after the Big Bang. Without dark matter, the Milky Way would not hold together. The stars at its outer edges would fly off into space because the gravity of all the visible matter combined would be insufficient to keep them bound. Every galaxy astronomers have measured spins faster than its visible mass can explain. Dark matter is the hidden anchor in every one of them. And yet, despite decades of increasingly sophisticated searches, nobody has ever directly detected a single dark matter particle. Underground detectors the size of swimming pools, filled with ultra-pure materials and cooled near absolute zero, have found nothing conclusive. The Large Hadron Collider at energies never previously achieved in a laboratory has produced no confirmed dark matter signal. Space-based observatories scanning for indirect signatures have yielded hints, but no confirmed detection. We know dark matter exists because of what it does, through the gravity it produces, through the way it bends light from distant galaxies, through the motion of stars that cannot be explained by any visible mass alone. The collision between the Milky Way and the Large Magellanic Cloud is now providing a completely new approach to studying it. The gravitational wake left behind by the Large Magellanic Cloud as it moves through our galaxy's dark matter halo, is a physical structure sculpted by dark matter dynamics. Its precise shape, how dense its core is, how sharply its edges fall off, how quickly it diffuses as time passes, is directly controlled by the properties of dark matter itself. Different theoretical models of what dark matter actually is predict measurably different weight characteristics. Cold dark matter, the model fitting most large-scale cosmological observations, predicts a specific density profile. Warmer dark matter, with faster-moving particles, produces a different and more diffuse structure. An exotic model called fuzzy dark matter, where dark matter behaves as a quantum wave spreading across enormous scales rather than as discrete particles, produces something different still, with wave-like interference patterns that particle-based models would never generate. By measuring the wake with enough precision using James Webb observations of outer halo stars, combined with data from the European Space Agency's Gaia satellite and large ground-based spectroscopic surveys, scientists can test these models using a natural experiment running in our own cosmic backyard. No particle accelerator required, no laboratory needed. Confirmed. The wake exists, its location matches theoretical predictions, and its detection provides independent evidence the large Magellanic Cloud is on its first orbit through our galaxy. Unknown whether its precise density profile is consistent with cold dark matter or points towards something more exotic. That question is being actively answered with data collecting right now. Physics could be rewritten by what our nearest galactic neighbor left, trailing behind it in the dark. And while the invisible yields its secrets slowly, the coming merger is about to produce something visible and spectacular on a scale that our galaxy has not seen in billions of years. A galactic collision looks, from a distance, like pure destruction. Two systems of hundreds of billions of stars crashing into each other. Structures built across billions of years being scattered and torn. Order dissolving into chaos on an enormous scale. It has the appearance of an ending, a final chapter for everything involved. But the physics inside a galactic collision tells a different and more complicated story. Collisions between galaxies are simultaneously some of the most prolific generators of new stars anywhere in the universe. The violence and the creation are the same event seen from different angles. Here is the mechanism. Inside any large galaxy, enormous reservoirs of hydrogen and helium gas float between the stars in clouds spread across thousands of light years. Under normal conditions, most of this gas is too diffuse and too warm to collapse under its own gravity and form new stars. It exists in equilibrium, stable and drifting, waiting for something to push it past the threshold where collapse becomes inevitable. Galactic collisions provide that push at an extreme scale and across enormous regions simultaneously. When two galaxies begin gravitationally interacting, their gas clouds do not pass through each other freely the way stars do. Stars avoid each other because the space between individual stars is so vast. Gas clouds, spread across thousands of light years, collide. They compress against each other, driving powerful shock waves through enormous volumes of material. Shock waves push gas density higher. Higher density triggers gravitational collapse. Collapse ignites new stars. In galaxy mergers observed throughout the universe, astronomers consistently find dramatically elevated star formation rates compared to isolated galaxies of similar size. Sometimes the increase is tenfold. In the most extreme cases, called starburst galaxies, star formation rates climb to 100 times normal or beyond, burning through the galaxy's entire gas supply in a fraction of its usual lifespan. The merger of the Milky Way and the large Magellanic Cloud will produce a starburst. Simulations consistently show this outcome. Gas from the Magellanic Stream is already beginning to fall into the disk, adding fresh fuel to regions that will eventually be compressed further by the merger dynamics. When the gravitational interaction between the two galactic disks intensifies, Shock waves propagating through the combined gas reservoir will trigger generation after generation of new stellar birth across vast regions of space that are currently quiet. Many of the stars born in this burst will be massive. They burn through their fuel in a few million years. When they die, they explode as supernovae, seeding the surrounding gas with heavy elements and sending fresh shock waves outward that trigger the formation of still more stars. Cascading waves of creation, following each explosive death in a self-reinforcing chain. After the most violent phase of the merger settles, the combined galaxy will likely enter a quieter period. Gas reserves largely depleted, star formation rates dropping toward the lower levels seen in older, more settled galaxies. The combined structure will appear redder and older, but during the merger itself, the Milky Way will be more luminous, more active, and more alive than at any point in its entire 13 billion year history. And what other merging galaxies across the universe reveal about how this process will look from the outside is something Webb has now shown in extraordinary detail. We cannot watch our own galactic merger in real time. 2 billion years exceeds every instrument and every civilization ever likely to exist on Earth by such a vast margin that no bridge between the present and those events can be built. But the universe is generous with examples. Across billions of light years of observable space, galaxies at every stage of the merging process are visible right now, each one frozen at a different moment in a sequence that unfolds across hundreds of millions of years. By studying them, astronomers can reconstruct the full timeline of what awaits the Milky Way, from the first gravitational distortions to the final settling of a combined galactic structure. James Webb has been systematically imaging some of the most dramatic of these systems, with infrared resolution that no previous telescope could provide. One merging pair sits about 120 million light-years away, two spiral galaxies caught in the early to middle stage of their collision. Their outer arms have been stretched and bent by tidal forces. A bridge of displaced stars connects them across the gap between their two centers. Webb's imaging, combined with observations from an X-ray space observatory, revealed concentrated knots of newly forming stars located precisely at the compressed boundary between the two systems, exactly where the shockwaves from the colliding gas are driving density past the threshold for collapse. Confirmed. This is what the enhanced star formation phase looks like when two galactic gas reservoirs begin pressing against each other. Another target, a compact grouping of 5 galaxies, roughly 290 million light-years away, was among the very first objects Webb imaged after beginning full science operations. Webb revealed an enormous shockwave spanning a region several times the width of our entire galaxy, generated by one member galaxy, driving through a stream of gas left behind by a previous interaction between two of its companions. The shock was simultaneously heating gas to extreme plasma temperatures in some regions, while triggering new star formation in compressed filaments running along its leading edges. Mystery. Scientists do not fully understand how a single shock front can heat gas to extreme temperatures in one zone, while enabling stellar birth in adjacent zones within the same overall structure. The physics of the boundary region between the two outcomes remains an active area of research. Webb has also provided observations of galaxy groups in the very early universe, just 800 million years after the Big Bang, where multiple galaxies were already merging into combined structures far earlier than any previous model predicted. Such complex mergers could occur. This tells researchers that what the Milky Way and the large Magellanic Cloud are entering is standard cosmic behavior across all of time. The Milky Way was built by this exact process, consuming smaller galaxies across its entire history. Traces of those ancient absorptions are still detectable in the halo today, identifiable by the chemical compositions and orbital patterns of stars that arrived from galaxies that no longer exist anywhere as distinct objects. What is coming is the next chapter in a story that has been running since before our galaxy formed its first spiral arm. And the most direct evidence that this story is already actively progressing comes from the physical scars the first encounter has already left permanently written into our galaxy's structure. The large Magellanic Cloud has already been here. Not in the sense of arriving at its final destination, in the sense that it has already made its closest approach to our galaxy's disk at a distance of roughly 50,000 light-years from the galactic center, and already continued outward again. That encounter happened in the relatively recent cosmic past, and the evidence it left behind is encoded in the physical structure of our galaxy in ways that instruments can now read directly. The most obvious scar is the warp in the outer disk. The plane of the Milky Way does not lie flat at its outer edges. It curves upward on one side and tilts downward on the other, a deformation that astronomers have known about for decades. Current models, incorporating the large Magellanic Cloud's revised mass and its calculated orbital trajectory, reproduce the observed warp with an accuracy that makes coincidence an implausible explanation. The first close pass deepened the warp, or potentially caused it outright. Beyond the large-scale warp, researchers have found wave-like oscillations rippling through the disk material. The Milky Way's gas layer has corrugations, periodic variations in density and height propagating outward, like rings spreading from a disturbance point, exactly as you would expect to find in the wake of a significant external gravitational event arriving within the past few 100 million years. Stars in the outer disk have been mapped, moving in complex patterns that deviate from simple circular orbits. Their velocities carry the signature of a system disturbed and still returning toward equilibrium, spread across the outer galaxy in the spatial pattern you would expect from a gravitational disturbance arriving from outside the plane. The satellite galaxies of the Milky Way have also been affected. Several smaller companions, orbiting at various distances, show orbital properties inconsistent with a system that has been isolated from significant external gravitational influences. The large Magellanic Cloud's passage appears to have perturbed their paths in ways that match the predicted effects of the first close approach. All of this is confirmed by observation across multiple independent datasets and instruments. The first pass changed our galaxy in real and measurable ways. The changes are too subtle to affect any human experience across any accessible timescale, but they are there, permanently written into the fabric of the Milky Way's structure, waiting in the data for instruments precise enough to read them. The large Magellanic Cloud is now moving outward again, retreating from its closest point back toward the distances where it has appeared in the southern sky across all of human history. But this retreat is not an escape. Gravity has already written the outcome. The cloud will slow, stop, and fall back inward. The second approach will be significantly closer. Each subsequent orbit will tighten further. James Webb has given scientists a sharper and more complete picture of exactly what is approaching than was possible before it launched. And the full account of how that telescope transformed our understanding of this collision deserves its own complete telling before this story reaches its final chapter. Because before Webb, the story had a shape but no texture. Before Webb, the details that turn a collision from an abstract future event into something real and present and already unfolding were simply not visible to any instrument humans had ever built. What changed when that mirror turned toward our nearest galactic neighbor is a story about what science looks like when the right tool finally arrives. Before James Webb launched in December of 2021, the story of the Large Magellanic Cloud collision existed mostly in outline form. Astronomers knew the merger was coming. They had rough timelines and mass estimates and orbital trajectories and simulation outputs built on the best available data. The broad shape of the future was visible in the numbers. The story could be told in broad strokes with reasonable confidence. What they did not have was the detail. And in science, detail is where everything actually changes. James Webb's primary mirror stretches more than 20 feet across, coated in gold to maximize its reflectivity at infrared wavelengths. It collects more than 6 times the light of its immediate predecessor. Its instruments extend sensitivity into wavelength ranges that no previous space telescope could access with comparable resolution. And crucially, it was designed from the beginning to penetrate the dust that had been hiding the inner workings of galaxies, star-forming regions, and galactic centers from every telescope that came before. When Webb pointed at the large Magellanic Cloud, it was not seeing the same object astronomers had catalogued across centuries. It was seeing past the curtain into regions that had been functionally invisible for the entire history of human astronomy. Inside a star-forming complex in the southwestern portion of the cloud, Webb found stellar birth happening at twice the rate anyone expected, driven directly by the gravitational compression our galaxy was already applying. Confirmed, the collision is producing enhanced star formation right now, not only in some future epoch, still billions of years away. Inside the Tarantula Nebula, Webb revealed thousands of previously invisible newborn stars and found that the statistical ratio of stellar sizes being produced differed from what models predicted for an environment this extreme. Confirmed and partly mysterious, even the most energetic star factory in our cosmic neighborhood produces surprises. At the site of Supernova 1987A, Webb found internal structures forming inside the expanding debris cloud that no previous telescope could clearly resolve, and began working toward a direct detection of the neutron star believed to sit at the center of the remnant. Confirmed, the remnant is still actively evolving nearly 4 decades after the explosion, contributing to the detection and detailed mapping of the dark matter wake trailing the large Magellanic Cloud through the outer halo. Webb helped provide some of the most precise constraints on the dark matter environment of our own galaxy ever assembled. Confirmed, the wake is real and carries information about the fundamental nature of dark matter itself. Each of these contributions changed a piece of the larger picture. Some confirmed what theory had predicted and placed those predictions on firm observational ground. Some added complexity where earlier models had assumed simplicity. Some opened new questions that are being actively pursued with observations still arriving from the telescope right now. Webb is still operating. Data is still coming in. Papers continue to appear, each one shifting some section of the story by small or large amounts. The universe is not running out of things to reveal, and the collision developing in our cosmic backyard is one of the richest and most productive sites of active scientific discovery in the entire observable sky. One chapter remains, and it leads to where this story has always been pointing. Go outside on a truly clear and dark night, somewhere far enough from any city that the sky is genuinely black, and the stars are numerous enough to be overwhelming. Look up. The band of the Milky Way stretches from one horizon to the other, a river of hundreds of billions of stars, each one a distant point of light, too far to visit, but close enough in the scale of the cosmos to be considered part of the same family as the star our planet orbits. This galaxy has existed in approximately this form for 13.5 billion years. It has hosted the birth of countless stellar generations, the formation of billions of planetary systems, and at least one civilization curious and persistent enough to spend its spare time figuring out what all those lights actually are and what they are doing. It will not always look like this. In roughly 2 billion years, the sky will begin changing in ways no human eye will ever see, but that physics guarantees with confidence. The large Magellanic Cloud, which has hung as a soft pale smear in the southern heavens across the entire span of human observation, will grow. As it spirals inward through successive orbits, its apparent size will expand. Individual stars within it will become visible to the naked eye from any world with a clear southern sky. It will spread across the southern celestial hemisphere, no longer a cloudy patch, but a detailed structure, a second full galaxy visible and close enough to resolve as something more than a blur. The galactic center will brighten. Sagittarius A star, fed by rivers of gas being funneled toward it by the growing merger, will transition from its current quiet dormancy into something blazing and active. For millions of years, the galactic center will glow with the output of an active nucleus, a persistent beacon visible in the direction of Sagittarius from any planet in the galaxy, with a clear sightline inward. New stars will ignite in cascading bursts across the disk. Regions currently cold and dark and quiet will become nurseries glowing with the intense blue-white light of massive, short-lived stars that burn brilliantly and then explode, seeding the next generation. None of this will be witnessed by anything we recognize as human or any descendant civilization we can meaningfully imagine. The timescales are simply too vast. What matters now is this. The gas is already falling. The wake is already trailing behind the large Magellanic Cloud through our dark matter halo. The center of mass of the Milky Way has already shifted. The outer disk is already warped. The companion galaxy is already being torn apart. The hypervelocity stars fired by the hidden black hole are already crossing the space between us and arriving. The scars from the first pass are already written permanently into the structure we call home. The collision is an ongoing process. Its physical signatures are detectable by instruments that exist today in a galaxy that is already responding to forces that began shaping it long before any human looked up and tried to understand what the sky was made of. James Webb gave us the sharpest picture yet of an event unfolding across timescales that dwarf everything humans have ever built. And what it showed is a universe that runs its largest experiments without waiting for anyone to be ready. The Milky Way is in motion. The collision has already begun, and we are inside it right now, looking up